Hi, and welcome to Geeks for Geeks. Today, we would be discussing the problem number of occurrence. So, this is a very interesting problem, seems to be a very easy one. But when we deep dive into this, this seems to be a very interesting problem. So, the problem statement is quite clear from the problem name itself. The question asks us that we are given a sorted array and you need to find the number of occurrences of x. So let's just quickly head over to the sample test cases. So very first, we are given the values 1, 1, 2, 2, 2, and 3. And the value of x that we need to find is nothing but 2 itself. So it can be figured out easily that the number of occurrences of 2 are 1, 2, 3, and 4 itself. So, talking about the first brute force solution itself, it is very easy that we can simply iterate over the array and then we can simply count all the digits itself. Okay, so let's say we got a 2, so we would increase, let's say we would just have a counter that if the current element, that is a of I, is equals to x, we would increment the counter itself. And that's how we would say that this is the number of occurrences of this instance. So what is the time complexity of this? So basically, you would be traversing on each element by using a for loop. So this would be big O of n. And at each element, you are doing a constant operation, that is just a comparison operator. So for one element, you are doing constant operation. So for n elements, you would be doing 1 into n operations. So in a nutshell, this is big O of n because ignoring the constant itself. So after give this solution to the interviewer, he would ask you to optimize this. So when asked about the optimization of this, you need to see that the array is sorted itself. So I would just give you the idea that whenever you are given a sorted array and you need to target some elements in the given array itself, I would suggest you that you should think in terms of binary search first. Like there should be a checklist in your head that yes, I would be first comparison, priority queue, sorting, and these all that. So this is a proper identification that this problem might be solved using binary search. Array, elements, and sorted. These three things together kind of tells us that it can be solved using binary search. Okay, so this is sorting. But binary search is searching an element in a sorted array. That is true. But it doesn't handle duplicates at this point. So you need to understand one small branch of binary search, which is nothing but lower bound and upper bound. So at this point, if you don't know about what is basically binary search, I would suggest you that you pause at this point and then go and learn binary search and then come back to this video, because the branch of binary search, which is lower bound and upper bound, would be discussed in this itself. Okay, so let's talk about how we can really solve it using lower bound and upper bound. So let's first talk about the definition. What is basically lower bound and upper bound? Lower bound is a person, okay, if it would search for an element. Both are searching algorithms. So lower bound would search the element. If it is present, it would return. So I would just mention the criteria itself. If that element is present, then it would return the first occurrence. If it is not present, it would return the next greater element itself. Okay, if it is not present, it would return the next greater element, that is NGE itself. Upper bound is kind of very similar to this, but you to remember this fact, you can just remember what is lower bound. Lower bound is nothing but a person who is good enough with his condition. He has some condition. If the condition is fulfilled, he would be happy in the first instance, that is the first occurrence. And if the person is not happy, he would kind of thrive more or work hard more. That is why he would go to a next greater element. But upper bound is a very ambitious person and he would also always go to the next greater element. So let's say in this array, suppose we have 1, 1, 2, 2, 3 itself. I do an upper bound of 2. He is a very ambitious person, so he would always go and target this 3 itself. Lower bound is a person who is happy if his condition is met. So the first point where his condition is met is this. So lower bound of 2 would point to this index and upper bound of 2 would point to this index. So you can just remember this with a good example, that what is lower bound and upper bound. You don't really need to just have the conditions in your head. You can just remember this funny example and then you can move forward. Upper bound is an ambitious person and lower bound is a person who is happy if his condition is met. Okay, a very simple person. Okay, fair enough. Now, how really is lower bound and upper bound linked with binary search? Okay, let us see that. Okay, let us draw the algorithm from the sample test cases itself. Okay, so let's say we have 1, 2, 2, 2, and 3. Okay, so if you know binary search, there are some key elements to this. Okay, that is, you would be declaring something known as low and something known as high. Low would be equal to 0, high would be equal to n minus 1. Basically these two elements. Okay, now the very next thing you need to do is something known as mid. Mid is equals to, here I won't be using the other formula, I would be using the simple formula, and it would work definitely. I have been using this for the last 4 years and it didn't make me worry, to be honest. So what is, so this would be low plus high divided by 2. This is what you do in a binary search. You have a low pointer, you have a high pointer, then you have a mid, which is nothing but the addition of lower bound and upper bound divided by 2. And this mid would point to some index. This mid would point to some element. And what are the elements that can happen? So it might be the scenario that the array A, okay, the array A of mid is greater than x. What is x? X is for which value we want to do the lower bound. So basically x is nothing. So we are learning lower bound at this point. Okay, we are learning lower bound at this point. So we are doing a lower bound of x, and it might be a scenario that the element current is greater than x. Okay, the very next case is A of mid is less than x. Okay, and then the very third one is A of mid is equal to x. These are the three things can happen. It can be either less, it can be either more, or it can be either equal. Okay, so let's hit the condition. Let's say if, so let's say this is low, this is low, so I would just write it with a different color so that it would be simpler to understand. So this is low, this is, let's say, high itself. Okay, fair enough. So now let's say if A of mid is greater than x, let's say we are doing a lower bound of 2. Remember this element. So A of mid is greater than this element. Let's say it is pointing up to the value 3. Okay, so if we want to find the first occurrence of 2 and then we are pointing to a bigger element, then we should go on which side? This is low and high and it is pointing to a something big element, and we want the first occurrence of that element. So if we want to find the first occurrence of x and we are pointing to 3, then this just means that low and high should be in this side, like the answer should be in this side, not on that side. So I can say low would remain the same, but high would become mid minus 1. Okay, because we want to find the first occurrence. So we know that the answer would exist in the left half. Let's say the element we are trying to find is less than x. So either the answer can be equal or either the answer can be greater. Okay, it can't be less. So greater elements are found in the right hand side, but still I would just show you. Let's say we are mid is pointing up to just 1. Then we should go to mid plus 1, that is low. We should make this low here only and high would remain at its position. That is why we would say that if a of I is less than mid, we would make low is equals to mid plus 1. Okay. At this point, if it is equal to x and we want to find the first occurrence, if let's say we are currently at this mid is pointing to this t, and we want to find the first occurrence. So if we have found an element and we want to find the first occurrence, it would lie on left hand side, that is this side itself. That is why we would say I should come to mid minus 1. So we would just write high is equals to mid minus 1. Okay, this is how I wrote the condition. At what possibilities I can save the answer? Either the answer can be just one element greater, or either it can be equal. We have answer is equals to mid. So at this point we would update, we have equal, so we would also update answer is equals to mid itself. And if it is less, less can never be an answer. That is why we would simply say this is, here we won't save the answer, rest in two cases we would save the answer. So basically this is the way. You don't really need to mug up the whole algorithm of lower bound. You can just remember binary search, how it works. If you have a good understanding of binary search, which is a very simple algorithm, if you write a sample test case, a very small sample test case, if you draw out the three condition, you can write lower bound in this fashion and upper bound in this fashion. So let's just implement lower bound and upper bound. But before that, let us first understand how lower bound and upper bound is coming to the picture. So if you see, if you just observe this, if let's say we are given 1, 2, 2, 3. So I want to find the number of occurrence. Let's say I want to find the number of occurrence of 2. So if I do a lower bound of 2, it would point me to this index, that is 0, 1, 2, 3. So it would point me to 1. So lower bound would point me to 1. And upper bound, what is upper bound would point, if I do upper bound of 2, it would point to the index 3. So upper bound would point to the index 3. So if you observe, upper bound minus lower bound is nothing but the occurrence of that, because lower bound would point to the very first occurrence of 2. Upper bound would just point to just after that occurrence. So in between upper bound and lower bound, all the elements except this lower bound thing, all the elements are the occurrence itself. That whole range would consist of the value 2. See, this is lower bound, this is upper bound, and whole range would consist of 2 instead of this. Let's just see one more example and then we would just implement this lower bound and upper bound. So basically, just before implementing, I wanted to show you why do we really need lower bound and upper bound and why we are talking about that. So let's just say we have 1, 1, 2, 2, 2, 2, and 3. So now if I do a lower bound of 2, it would point me to this index. If I do an upper bound of 2, it would point me to this index. Now you can again see in a large value, this is 0, 1, 2, 3, 4, 5, 6. So basically we have 6 minus 4, 6 minus 2, that is upper bound minus lower bound is equals to 4. Yes, this is the number of occurrence of 4. This is how we can do a combination of lower bound and upper bound, and we can find the number of occurrence. So basically lower bound and upper bound are siblings of binary search. As they are siblings of binary search, so time complexity would be log base to n. So lower bound and upper bound, it would be 2 multiplied by log base to n. So if we implement it correctly, time complexity would be having log n, because the constants are ignored at this point. So yes, this is much better than big O of n. No auxiliary spaces are required, because in spite of the number of variables we use, if we don't use any auxiliary space which is dependent on a variable, we won't really require it at this point. So basically the time complexity is log n itself. So we know this lower bound. So I would implement this lower bound, and let's just see. So I'm a very lazy person, so I would just make this as array A, and let's implement this. So it would return me an index, and I would just name it as LB. I would take an input of the array, I would take an input of the size, I would take the number that I want to find. At this point, I would say int low is equals to 0 and high is equals to n. I wrote n minus 1, but here I am writing high. because in binary search the search space is 0 to n minus 1. But in lower bound, let's say I have something like 66666, okay, and I want to do a upper bound of 6, or let's say a lower bound of 7. If I do an upper bound of 6, it should point me to this. Okay, that is why I am doing this at this point. Okay, so now I can simply say high is equals to, let's make this as n minus 1, and we would initialize, if the answer is not updated, we would initialize it with n. So that is the reason answer is equals to n. So this value would never get targeted if, let's say, we are trying to find 7. So this lower bound would die, but the updated answer would be n. That is why we are initializing this with n. And we would say while low is less than equal to high itself, okay, we would initialize mid, and mid is equals to low plus high divided by 2. If a of mid is greater than the value x, where should we move? Let's go back till this point. Where should we move? If a of I is greater than x, high is equals to mid minus 1, and we would save the answer. Answer is equals to mid. Okay, and then we would write an else if condition. If a of mid is less than x itself, we would make low is equals to mid minus 1. Okay, here saving of answer is not required. The last, very last condition, if it is equal, we would say high is equals to mid minus 1, and answer is equals to mid itself. Okay, at the end we would just return the answer itself. So here we would just use upper bound minus lower bound, and it would give me the answer. Now let us quickly see the conditions for the upper bound also. Okay, let's say we found a value which is greater, and upper bound was what? So this is now upper bound. Let me just remove this. Upper bound of 2. Let's say we want upper bound of 2. What was upper bound? A very ambitious person, just one element greater. So if we found a greater element, so it should be just one element greater. It might be the scenario that the array is 6, 7, 8, and we are at 8. So just one greater element would lie on the left hand side. Left hand side means what? The high would go here. So high is equal to mid minus 1, because a better answer can exist at that left point if the answer is less. So we are trying to find a value greater, and this is less. There is no value, just make the low go to this side. We want a greater value, so we should go on the right hand side. If we want to go on the right hand side, we should make low is equals to mid plus 1. If it is equal, if it is equal, it is equal, but we want one element greater. One element greater element would lie on the right hand side. Right hand side means what? This is high, this is low. So right hand side means low would come to this point. Low is again equal to mid plus 1. Low is again equal to mid plus 1. What all answers can be our probable answers? So a value greater than x is our answer. So we would only save the answer in this condition. Rest all condition can never be my answer. Okay. So let's implement upper bound also quickly. We would just do a copy paste kind of thing as we did in the scribbling. So we would make, if a of mid is greater than x, we would make high is equals to mid minus 1, answer is equals to mid. We don't really need to change anything. Low, we would go to low is equals to mid plus 1, and else in all other condition low is equals to mid plus 1, and we won't save the answer in this scenario. And this is done. Now we would simply call return upper bound, and this would be just ub. Okay, ub upper bound of a comma n comma x minus lower bound of a comma n comma x itself. Okay, now let's just compile and run and see how many errors are we making. Okay, seems like we made an error or something. We can simply do a lower upper bound of a comma n comma x and lower bound of a comma n comma x, and this should definitely work. Now let's just compile it and see how many errors are we making. Okay, seems like no error is being made. And yep, we got an AC itself. So there are two small things that I want to tell you. The very first one is you can count the number of occurrences even by using a hash map if there are multiple elements. If one element, we can simply use a variable. The very next thing is this condition low is equals to mid plus 1 can be accommodated in one else itself, but I tried to make it as intuitive as possible. You can simply draw out different cases less than equal to or more, and you can do the same copy pasting thing for lower bound and upper bound, and it would work as law. And the same implementation you can carry on with binary search itself. So that's it for today. Thank you.